I think she's having issue.
Hey, Flatzoid.
Ah, there we go. How are you going?
Yay!
I
I have to disconnect and reconnect.
I hope you're doing well.
Can Rachie hear
Yeah, not
us?
too bad yourself.
I'm doing well, thanks. No, I don't think Rachie can hear you guys. They were asking Ellemnet if they can hear you. Said no.
I can only hear you.
Yeah.
Okay.
So, yeah, thank you for coming. Because, like I said, I just want to get your side of the story on everything that's going on. And
Before you start, will you just pass a message on for me?
Yeah.
Tell Rich I'm honoured that I'm second video since she became a baller.
Michael said he's honoured that he's on your second video since you became a baller.
Oh, he's welcome.
So yeah, like I said, thank you for coming. I also want to hear your side of the story, and what's your thoughts and why, what made you change your mind, kind of thing.
Well, the thing is, people have been saying I'm back on the ball in that, but I didn't say I'm actually back on the ball. You know what I mean? I didn't say that I'm a Glober now, but people have like misunderstood what I've said or something, and then they're spreading that, and then people ain't actually watching the video and actually seeing what I've saying. You know what I mean?
Yeah. Okay. Yeah, that's what I say. I want to hear your side of the story because yeah, everywhere we're getting is like even from FTV side, it's like you got back to the globe kind of thing. And it was interesting when Anthony said, no, that's not exactly what you said. You're just stepping back a bit because of all the infighting and everything. So,
But yeah, stepping back, and obviously since stepping back, I've realised that there is a lot of misunderstandings, and then to me, there is more evidence of the ball than there is of flat Earth. But that doesn't mean I'm back on the ball.
well, would you be able to maybe give us some evidence of what you think would be for the ball?
Yeah, like with the video, I saw you showing a bit of it. With Michael Kahn's video, he showed that as you back away on a flat surface, the angle decreases, which is fair enough. Everybody will agree with that. But when he backs away in 10 centimeters or 10 inches, whatever it was, it doesn't drop by the same amount. So on a flat surface, you can't show that something will drop by the same amount of degrees for the same amount of distance.
Okay, but you do know that's on small scale though, and it's
Yeah,
not through a lot of atmos, as you could say. I mean, when you're looking at a star, you're looking through a lot more atmos, and you're looking with larger distances. So parallax also plays into account. So that's why you have differences. But what he's showing on small scale, and like I was explaining, does show it just on a small scale to visualize it drops apparent, not physical.
Yeah, well, everyone will agree they drop like apparently on a flat surface as well. It's just they don't match, you know what I mean? Whereas with a sphere, it does match up until when it gets to the horizon.
It doesn't match with the sphere. That's the whole issue.
Flatzoid.
Yes, Michael.
Flatzoid. Ask Rachie if she can demonstrate that in small scale.
Yeah, Michael's asking, would you be able to demonstrate that in small scale for the globe?
No, that's
Try.
That would be great, yeah.
I've never actually tried. I've only done the math, obviously, based on the sphere and that. But yeah, I could actually try and do a demonstration on that.
But also, you do know for your globe, I'm not saying your globe, sorry, the globe. Let's take Polaris, for instance, and you go away with latitudes. You do understand the globe is a spheroid. It's an oblate spheroid, so it has different radius values. So it's not supposed to drop exactly as what they put it as linearly. It will drop different as well on the globe because you have a different elevation.
Yeah, but it's only like 14 or 28 miles, isn't it? Out of like, what is it, 6,000 something miles for the equator? For the diameter?
Yeah, it works out to like 48 kilometers or 24 kilometers difference than what it would be at...
Something like that.
Yeah. So...
Can I just ask one more question and then I'm done?
Okay, Michael wants to ask one more question.
Yeah? Explain how you were able to use a protractor with a flat bottom on a curved ball to measure an angle.
Yeah, he's asking how are you able to use a protractor with a flat bottom on a curved ball?
Because like that Protos had screenshots, when you take it on a small scale, which obviously it is a small scale that you're on compared to if it was a globe, you're on a small scale, do you know what I mean? So it seems flat, and therefore it's you could take a straight line. And the angle, the baseline doesn't need to be that long in order to get an angle. Like, you can literally use your fingers to get an angle. Like, it doesn't really matter how long the line is.
So you're saying you can create a chord?
No, because you don't need to create a chord, do you? It doesn't matter how long the line is. The line doesn't really have to be that long. It could be like a few inches. It doesn't need to be that long.
Yeah, but that's the thing. If you're saying it's because of Earth on Earth's surface, you have to use a chord, because that, if you didn't realize, that protractor you're using has a flat baseline, so that has to be parallel to the surface, and because it's not, the surface is curving away, it can't be parallel. So therefore, you have to have a chord which is cutting through the Earth's surface to give that angular measurement.
Well, no, it doesn't need to cut through the surface. Like, the protractor didn't cut through the surface. It's because you've got different verticals, you've got different horizontals. So as somebody said on the chat or wherever, it goes out almost into space. Do you know what I mean? What they call space.
Yeah, I'm gonna try draw it on. See if I can draw it on.
That video by
Sorry.
that AutoCAD video of Flatzoid.
Yeah.
No worries.
Let me just quickly.
Rob Durham, he explains why.
Mm-hmm. Okay, I'm gonna quickly try draw it for you on. You see, if you've got a globe like this, you got your sphere, and you're holding the protractor, okay, and you measuring, let's say like that. You got your angular reading. Now this is the bottom of the protractor, because you can imagine the protractor's going like this. You got me? So we've measured this this angle. Okay. Now the thing is, what the globe suffers with is, you got a zenith angle here at 90, and you're supposed to have the same plane for the zenith angle for the star. So if I got the star, let's say there, and it's supposed to be a 90 degree to the Earth, that means that the star doesn't have a 90, because look, it will go like this to the center, just like the globe is going to the center of the zenith. Now you do understand this is not a 90 degree angle.
Yeah, but that's like triangulation. They don't claim triangulation on the globe.
No, this is the circle of equal altitude. It's not.
No, the circle of equal altitude is based on like what I did. Like, you draw a circle on the globe, and then it's the same angle from everywhere on the circle. No, it's just the same angle everywhere on that circle.
It's the same azimuthal plane.
No, that's not what they claim. No.
Yes, it is.
And that's not where I showed.
The circle of equal altitude is on the same azimuthal plane, Rachie. Even that, when you put that cup over, let's say we put the cup over and it comes here, okay? Let's say that's the cup's rim now. You do understand that's a chord, because the observer would be here and the star would be here. It's the same plane.
It's only a chord if you go through the Earth, but they don't. They use a tangent. No, they don't go through. They use the tangent.
But that's what a circle of equal altitude was. When you're putting that cup on the ball, you are making a chord.
No, the circle of equal altitude is basically like a circumference around it. So it's like a circle around it.
Ask if GP's on it.
That's their circle of equal altitude. So that you have the same angle on that circle around it.
Yeah, but that's what I'm saying. It has to be on the same plane. You would agree that on that cup you're using, for instance, that GP of the star and the GP of the observer is on the same plane. The same elevation plane.
The same plane if you cut through it, but they don't cut through it to use the plane. They use a tangent, don't they? So it's a tangent to it. They don't cut through the sphere.
Okay, but
they go around the sphere.
No, but you see, if you got that GP, you do know it has a line of sight to the GP from the observer.
No.
Yeah, because you can see the star. You're measuring an angle to the star, and that star has a ground position, which means it's on the ground, and that is on the same azimuthal plane as the observer's GP.
I don't know what you're actually saying there. No, I don't think so.
What I'm saying is, because of your globe, if you're holding a protractor above the globe, you don't have a 90-degree angle for the star like you have a 90-degree angle for the observer, They're not on the. They don't make 90-degree angles. And for a circle of equal altitude, you need the GP of the star to be a 90-degree on the same azimuthal plane as the observer as a 90-degree.
For them, that I don't know. On flat Earth, yes, but on the globe, no.
On celestial navigation.
On celestial navigation, they don't use the 90-degree like that. It's the 90-degree for the vertical from the observer.
They do.
No, I'm pretty sure it's 90-degree from the vertical of the observer, and then you use the.
Why do you think? Why do you think they try and make it a tangent? Because they need it to be a 90-degree on the same plane. So they need a tangent. But now we want to ask: is the tangent, the star's GP on the same tangent as the plane of the observer's tangent plane?
And they'd say no.
So then it can't work on a globe then.
No, because it works on a globe because it's a different tangent. They use different tangents all the way around.
Sorry, what? But it's not a. So if I
Disco ball there.
Yeah.
So if I measure a star's GP, which is on the same azimuthal plane as me, it means. I'm sorry, you're confusing me now because you can't have a different tangent. It's the same tangent plane.
Not for the globe because they have different tangents.
I agree, not for a globe. I agree, not for a globe. That's why they make a chord. Why do you know what an equatorial plane is?
Chord to the center.
That's what cuts through the Earth, isn't it?
Yeah, equatorial plane. Remember where they bring the angle down to the center of Earth?
Yeah, they can use that to get the angle because it's the same on the surface.
Yeah. So when they bring that down, that's why they got what they called a rational horizon. Because they need it to be parallel horizons. They need the GP of the star to be on the same plane as the GP of the observer. Otherwise, you won't get an angular reading.
But you can still get an angle even on a curve, so I don't know. I don't know if I agree with that.
No, you don't get an angle. You need the baseline to be straight. That's the whole point. That's why when they put elevation angles, the baseline has to be flat because that's why you want a tangent, because you need a straight line.
Yeah, but like I said, this tangent doesn't need to be that long, does it?
A tangent is just a point with a straight line on a curved surface. So that's what I'm saying. If you got a tangent, you do understand your tangent would be a different tangent to the star if you're on a globe, and you can't see the star's GP on a globe, so therefore you can't have a tangent to the star.
Well, only if it's in view, obviously. If it's gone beyond the curve, as they would call it, then obviously you won't be able to see the star to do the celestial navigation. But that goes for flat Earth too, because if it's out of your view, you can't see it, can you?
No, it's on the same plane. You don't need to see a GP for the star. You see the star and know it's straight down is on the same azimuthal plane as the observer. Do you know what an azimuthal plane is though?
It's the same vertical, isn't it?
Yeah, they got the same plane.
On the same baseline.
Maybe I'm going to stop sharing. There we go. But yeah, that's interesting because that's what I was trying to explain. The globe doesn't work. I'm going to see if I can get azimuthal plane. Okay, I'm going to see if I can share the screen again quickly for you. Let's see. There we go. Go live. You can see this, correct?
1 sec. It's loading. Yep, that's it.
Okay. Oh, is it still showing?
Yeah, I can see it.
Okay. Anyway, you can see this azimuthal. It says azimuth.
Yeah.
This whole plane, this whole circle, that's an azimuthal plane. You can see the zenith of the observer is on the same azimuthal plane as the star. You get it? It sits on the same plane.
Yeah, but see that azimuth?
Yeah, that's just the left to right.
As you go, as you go around, that would be the outside of the sphere, so that circle would be going around the sphere.
Remember,
so that's the azimuth.
Yeah, but remember I asked you, are they creating a chord, or do they have a tangent, the same tangent? They can't have the same tangent on a globe. So either they're making a chord, or they have the same tangent, which is impossible.
Yeah, but they're not making a chord. So from that azimuth, if you imagine you was on that azimuth, so say where the pink triangle is, the pink arrow, if you're there and then you drew a tangent out, then you get your angle from that to the star, which is up in the sky.
But look what I'm saying. The observer has exactly the same equatorial azimuth plane as the star. It falls on the same plane. So the zenith is a 90 degree for the observer on the same plane that the star has a 90 degree zenith. It's on exactly the same plane at a horizontal baseline. So if you're claiming it's not a chord, then how are you claiming they have the same tangent if they have two different zeniths?
I'm not claiming they have the same tangent, I'm claiming they have different tangents.
But you require the same tangent to have the angular reading. This is exactly what's shown on here.
Well, not really, as I showed with the screenshots, like on the ball. I had different tangents at different places, do you know what I mean, around the circle.
But then it's a chord, which you're saying it's not.
But it's not a chord, because I wasn't using a chord, was I? I just used a protractor, and the protractor went out into what you would call space, do you know what I mean?
Yeah, but then it wouldn't be on the same tangent. Exactly. You can't get it. I mean, you require... I don't know how I can draw this and make this clearer. The observer has exactly... You see my mouse? It's moving along the same horizontal plane, which the star has to sit on exactly... The GP of the star sits on exactly that same horizontal plane. If it sits on a different horizontal plane, aka a different tangent, it's not going to have an angular reading.
But if you take that azimuth, that is the circle that goes around the globe. So anywhere you draw a straight line from there will be a different tangent anyway.
No, it's the same equatorial plane.
Yeah, a plane around the sphere is in a circle around the sphere, but not the same
tangent. Remember your video? You showed putting a cup on an orange.
Yeah, that's the circle going around. That's the equatorial plane basically going around the circle.
Okay, now
around the globe.
Let's see if we can show this again. I think we should Rachie. Rachie. Sorry, I just want to quickly get your video up again. Gonna get the orange so I can show you, because this is just waiting for them to quickly put the cup on. There we go. Come put the cup. Okay. Let me quickly share the screen again. Go live. Okay. You can see the screen, correct?
It's loading. Yeah, okay. Can see it.
Okay. You would agree, they've put the cup now. There's a bulge inside this cup.
Yeah.
So, if it has the same azimuthal plane, it creates a chord through that orange.
Well, yeah. If you was to use the plane that's cutting through it, yeah.
So then again, the globe needs it to be a chord, or it won't work. And the globe doesn't use a chord for this celestial navigation. That's why we say the globers are creating a straw man here, and they are actually throwing celestial navigation away when they do this, because the globe is claiming a curved baseline.
But yeah, but you see that circle that's going around it?
Yes, the circle of equal altitude, which is, you just said now, it's a chord because it's cutting through. Remember, this observer is on the right here. The GP is on the same azimuthal plane as the star's GP. It's a straight line from there to there. It's a chord then, and the globe doesn't use a chord.
No, because they'd use a line going off the circle. As in, if it was going out into space.
It can't
you
go into
imagine
space.
that the keyboard was like space.
It requires the same plane, the same circle, you've got the same azimuthal plane. So if it's on the same azimuthal plane and you're claiming it's not a chord, then it's not a chord, then it's not a separate tangent, because they need to be on the same horizontal plane to get the angular reading. Because my 90-degree measurement of my GP needs to measure up to the 90-degree measurement of that GP of the star. If it doesn't measure up on the same plane, we're going to have different angular readings and we won't be able to get our distances.
I know what you're saying. I'm trying to rectify it in my head.
See, even the Globers in chat now are saying that's not how celestial navigation works. Exactly.
Yeah.
I don't know how much more simple I can make it. I am trying.
I was really hoping she'd come with something good, and she's come with nothing.
Yeah, I'm just trying to understand your point, you know what I mean? Like, because they say, like, you know, they use a circle of equal altitude, and then obviously they use a tangent on the circle of equal altitude, so...
Yeah, but that's the point. They're making the claim they use the same tangent. They can't use the same tangent. So it either has to be a chord or it has to be the same tangent, and both of them are impossible on a sphere surface. So therefore, you can't get the angle reading. Yeah, Michael.
Can you ask her when she's saying there? Was she talking about ballers or celestial navigation?
Michael, when you say they, are you asking who you're reserving to ballers or celestial navigators?
Ballers. To be honest, I haven't done much celestial navigation research, so this is like definitely a weak point of mine. But
tell her Michael says
just from what I've chatted to Globers about, so
yeah. But
and how I've like interpreted with what they've said, though.
Yeah, but I think you might have to go look more into the subject, because it clearly does need the same azimuthal plane. This is exactly why they have to have a more than one horizon. They have the visual horizon, sensible horizon, and the rational horizon, because the rational horizon is from the equatorial plane through the center of the Earth, because they need them to be parallel. If you have different tangents, you don't have parallel horizons, so you can't have the same angular reading, and therefore your GP of the star can't be a 90 as well as the observer, and it can't work on a globe. That's why when they put this cup over, it's just them showing they don't understand celestial navigation, because all they do, and they're just having straw man arguments debunking their own argument. That's why the GP is very important.
See, but this is the thing though, and they claim to be able to get a fix within like 25 miles, if not less. Whereas no flat earther has ever actually done that. So it's like, well, if it does require a flat earth, and flat earthers actually know how to do that, then why can't they get the fix within 25 miles when a glober apparently can, and they apparently use the globe?
Anybody can get that fix. The only difference is when we have strawmen like from the globe side saying you can't use an almanac because they say it's globe-based, which is false. Just means you're not using flat. I mean, even Brian Leake did it, and he got 11 kilometers away, and then they said, oh, but you used a globe data. You understand? So it doesn't matter who uses what. At the end of the day, it requires flat geometry for the celestial navigation to work. I don't know if you know who the Phoenicians were. Do you know who the Phoenicians were, Rachie?
No, I don't. No.
They were about 2,000 years ago, when they were also flat earthers, and they were one of the best celestial navigation civilizations around. They were very notorious for doing celestial navigation over the Pacific Oceans, using practically just their hands to measure angles between the horizon and the stars, because they memorized the positions of the stars in certain places, so they knew exactly where to go. This is all done using flat Earth. It wasn't. Remember, this globe data you're relying on comes from thousands of years of observations. It's not actually a globe. Now, because they can calculate it as a globe, doesn't change the fact that it was observed for centuries and then mathematically inhabited on a sphere for them, because we see in three-dimensional space, which is perspective. That's why we say it's just perspective hijacking.
Yeah.
Yeah.
Sorry, I'm just looking at some images now, but yeah, I can't really see anything that.
Yeah.
Where I'm trying to.
But But I think maybe go look more into it. You'll find it's very interesting.
Yeah, I definitely need to look more into it. Like I said, that is one of my weak spots, the celestial navigation. The only thing that I had with that was obviously, the 60 nautical miles or 69.1 69.1 miles per degree.
Yeah, and I can explain that as well if you want to. The 60 nautical miles is just based on a section of a circle. So when we look out in the sky, let's say we look at Polaris, and you see it's dropping the 10 degrees every distance, every 600 nautical miles. It's based on your perception, so you perceiving it. When I observe it, I'm looking at an apparent altitude of Polaris based on from me. So that's why every 600 nautical miles you're going away, it drops 10 degrees, just like you would expect, because that's how we observe it based on the perspective. Now they go and say, oh, but you see, you need it to be linear, so therefore let's make the surface transpoded from the sky, the celestial sphere. They've hijacked perspective for this. Now, remember, the 60 nautical miles is just based on a section of a circle, 360 degrees. So you would agree that in a circle you have 360 degrees, so that's a line segment from the radius outwards. I might have to draw this as well, I think, on paint as well for you. Let's see if I can get paint up. Where's my paint? There we go. I might have to draw this because... okay.
No, just saying. What?
Okay, this is a circle. And you would agree you have a circle is usually based in a quadrant kind of thing. Now, every degree measurement is going to be from the center of the radius outwards. You would agree with that? So it's a degree, 2 degrees, 3 degrees, blah, 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 making 360 degrees.
Yeah.
Okay. Now, have you ever realized that when they do this, looking at Polaris, for instance, say, okay, now we've measured Polaris at, let's just say, just say 35 degrees. It doesn't matter. It's not to scale. Do you know why they go to the center of the globe when they do this?
I know the flat earthers say it's because they need a flat plane, which makes sense, but
yeah, they did.
I don't know why they claim that.
It's because they need this relationship of the arc, which you observe, to be transposed from the celestial sphere. That's why they have the celestial sphere, and they just transpose it because they need it to have a linear relationship.
They use the circumference, yeah.
Yeah, so they need the relationship to be linear. That's why. So they're literally taking the celestial sphere and moving their position that was on the globe to the center of the sphere, so they can move the celestial sphere to the surface. So they're making the surface curved based on the celestial sphere, which is curved due to vision. And that's how they get their 60 nautical miles, because it's just a section, a degree in a 360 degree circle. It's like a clock.
Yeah. Yeah, it makes sense.
Yeah. Anything else?
Now, other than obviously the black swan and things like that, I disagreed with as well.
Oh, yeah. Well, what do you disagree on the black swan, though?
Well, the black swan says that, about the geometric horizon, and it ignores air, doesn't it? So we know that there's refraction, and it ignores air. So yeah, obviously, it's a kind of a straw man to say that the horizon should be there when really, there's air, so therefore it should be different because of refraction.
Not actually. The thing is, when it comes to, you've known like my 11 frames thing, where I took the inferior mirage out, because we're trying to show that the horizon is not physical; it's only an apparent position, so it's only optical. Now, the black swan works on the premise that they have that the geometry has limitations on a globe. So if it's set at 395 whatever on a globe, geometrically it can never change. You do know that when they took their measurements, even Aristophanes, for instance, he didn't take refraction into account.
Yeah, but he didn't really need to, did he? Because he used the dip of the horizon. that I say, and fucking sorry, swearing. And
he never used any dip of the horizon. He used a flat baseline to make an angular measurement based on assuming the sun's rays are parallel.
Did you say Eratosthenes or the other one there, Alberuni?
Alberuni also never used refraction, but Alberuni, very interesting, had to use the triangle method to get the height, just like that maths people for the shard, where they try to measure the height based on their angle reading to it, which is flat baseline, and then calculate the radius using the Haversine formula based on that. But you know there was no
all
refraction.
I know about Alberuni is, all I know about Alberuni is that he measured the height of the mountain and then went up the mountain and then used the dip of the horizon, which when doing the calculations on it isn't much.
No, Alberuni took a measurement at, let's say, 100 meters away to the top of the mountain, and he went a further distance away and took another measurement, so he would have recurring angles to be able to work out the height. Now he knows the height. Then he used the Haversine formula based on that height to work out the radius of the Earth. So he calculated the radius of the Earth based on a flat Earth measurements.
Where he went up the mountain
without
and
refraction.
then used from where I'm aware, he went up to the top of the mountain and then used the dip of the horizon, which from, I think it was 1,500 feet, the mountain that he was meant to be on. And it was obviously the dip of the horizon compared to refraction, and non-refraction isn't really that much. In degrees, I think it's 0.005 or 0.05, something like that. So it isn't really much with refraction in there with the dip of the horizon, so therefore it wasn't that far off.
Okay, but that's what I'm asking you now. You claiming the horizon is physical then, when Alberuni went on top of this mountain?
No, because the refraction from the geometric, if it was a globe, to the refracted, like I said, it's only 0.0. I can't remember if it was 0.05 or 0.005, something like that. I did the calculations on it the other day. But it basically is, it's less than a degree, you know what I mean? It's really, really small. It's like 0.0 something.
Yeah, but you would agree then the horizon's only optical, not physical.
Well, yeah, with refraction, obviously.
But there's always refraction. We don't have a day where there's not refraction. Because you're always
I agree with that, but
yeah.
That's why I disagree with the black swan, because the black swan ignores refraction.
No, it doesn't. That's the whole argument, because that's why we say when you say refraction, you're throwing your own geometry out of the water. Because as soon as you say refraction, you're saying it's not geometrically physical, it is optical. So therefore, the globe is not a physical Earth curve, it's only an optical phenomena, aka perspective.
Oh yeah, I agree with that. I think I'd agree with that too as well, because you can't see the geometric because of the atmo.
Yeah, so that's why it's not a straw man, because it's pointing out specifically, you based on your geometry, it overcomes the geometry of the Earth. So if you're claiming, okay, refraction, great. So then it's not a physical curve, it's only optical, and therefore it can't be your geometry based on 3965, because it overcomes that even with your super looming extra refraction, or what that doesn't exist, because you do know terrestrial refraction is an actual refraction, correct?
No, I'd say it's refraction because it's obviously different densities, wouldn't it?
Now, have you shown Snell's law? Have they shown Snell's law for terrestrial refraction before?
I couldn't say if they have or not. All I know is that obviously if you're doing a straight line as a light, if you was light basically going in a straight line, you're obviously going to meet less dense air at that point, aren't you? And then it bends down to the more dense air, because if you was going tangent to the surface, obviously it's becoming less dense the further you go out. Because obviously the air's stopping away from you.
Do you know the refraction Snell's law? In other words, do you know the Snell's law equations?
Not off by heart now.
No, okay, but you do know you require an angle from one medium hitting at a coincidence angle and then meeting at another medium. So you require two mediums.
Well, the change in density requires these two mediums, isn't it? So if you went from a more dense to a less dense, obviously that's like two different mediums, even though it's the same medium, it's changing density.
But the thing is you need two boundaries. So you need a boundary. So if I look through, for instance, a piece of glass, and it has water inside the glass. I have an incident angle that hits that glass and then changes the outward angle. That is refraction. With the globe, you don't have that. Terrestrial refraction doesn't actually do that. Terrestrial refraction only changes the shape of the geometry. It flattens out the geometrical shape. It doesn't have any light refraction at all. You might have to look up terrestrial refraction and you'll see there's no anything got to do with Snell's law at all.
I don't know. All I know is that they claim a difference in density, and obviously different in density changes, like with the sugar water. So it bends down, doesn't it? Like the laser light when Brad Vlad said, lasers don't work like that kind of thing.
Yeah, but like I'm saying, you can't claim refraction if there's no refraction. You need to have Snell's law for the refraction to work. But the globe model uses geometric flattening, so it literally grows and shrinks the geometry of the globe to make it work. So it's not actually doing anything other than changing the physicality, the physical shape of the globe. That's why the straw. That's why the black swan. But that's why the black swan is not a straw man, because it shows when you claim the geometry because of refraction changes, you're taking physical geometry and changing its limitations because of an optical effect. So therefore, your geometry is not valid, and your globe is not physical. It's only an optical effect.
Well, that's what they claim, ain't it? They claim that it flattens out the globe because of, the light bending down, going over the curve.
You can do that. We can go to Mick West's calculator. You can go to practically any globe calculator. They show you. There's no light refraction in there at all. It's all got to do with the Earth changing its shape. When you take the slider, even for, I think it's Mick West's, and you move it up and down, you see the globe flattening out. Its geometry physically changes. It changes its radius. It doesn't change the light. It changes radius.
Does it change the radius, or does it just changes what you see and it makes it rise up appearing flatter?
Do you understand?
But it doesn't actually get bigger.
It does. It changes the radius, the actual radius of the globe.
No, it's because there's a change in wave speed. So as obviously if you go into more density, then you go into less density, then it bends down to the more dense, and then obviously it's bouncing between the particles, changing the wave speed, and therefore refraction is a change in wave speed, isn't it? So if you've got more or less particles, obviously the wave speed is going to change because it's bouncing off more or less particles.
I agree. In reality, we got refraction. That's with Snell's law, but the globe doesn't have light refraction. It uses terrestrial refraction. Terrestrial means ground.
No, Earth, isn't it?
It's terra firma, terrestrial. It straightens out the globe. It makes its geometry bigger or smaller based on optical effects.
Makes it appear, yeah, but it doesn't actually make the globe bigger.
No, it literally makes it bigger. It changes the radius value. That's what the math does. It doesn't actually show anything refraction based. It's literally changing the radius value, and that's why when you say that black swan is a straw man, you're actually not understanding that when you say refraction, you are throwing away the globe's geometry. Then it's not a straw man. It's literally throwing away the math for the globe.
Well, no, because refraction is based on the geometry, isn't it? That's why you got 7/6R, R of the radius.
7/6R is not light refraction. That's what I'm trying to tell you. There's no light refraction for 7/6R at all.
Well, that's how much it bends, isn't it, by the math?
Let's try. I'm going to see if I can make it a visual for you. Let's take a balloon, for instance. A round balloon, okay? Or a ball. And you blow it up. You can physically see it growing in size now. Okay?
Yeah.
The radius is changing for that ball, correct?
Yeah.
That is how terrestrial refraction works. They have to change the radius value to fit the optical effect.
No, the optical effects makes it appear like the radius is bigger, but the radius doesn't actually get bigger.
Okay, then I got another one. because you're not going to get it. But I got another one for you. You saw that photo where the horizon is behind the oil rig that's blocked by the supposed Earth curve, correct?
Yeah.
Can you explain that if it's a geometric horizon blocking, if it's blocked but still the horizon's behind it?
Well, that's a straw man because it isn't geometric. That's the point I'm trying to make. You're saying, like, can you explain that as geometric horizon, but we're ignoring air at that point. We have atmosphere, which makes it refraction.
I don't think you understand. If it's the physical Earth curve blocking the bottom of the oil rig, okay, you would agree that would be physical Earth curve blocking the bottom of the oil rig.
With refraction, yes.
With or without, there's always refraction. Why is it that it's blocking the oil rig, but the horizon is still behind it?
Because of refraction.
So refraction can still block things while it shows a horizon behind it blocked because of Earth curve.
Maybe I'm missing your point. Can you say that again?
Okay, I want to see if I can draw it on. I might have to get the photo as well. So you might see. Let's see if I can share screen. Share screen again. Wonder can I just share my whole screen? Yeah, screen one. Okay, there we go. Okay, so Taboo conspiracy. Oh no, it's not this one. Sorry, I'm just quickly looking for that photo. It's on my channel. But I appreciate you coming on again.
Appreciate you having me on. It's been a long time coming.
But like I said, I'm not here to slag you off or anything. I'm just interested to figure out why you decided to do what you do.
No, I appreciate that. It's been a good conversation.
But it's good. It's good to see you at least open to discussing everything. So that's a good thing. Because a lot of people just decide.
Yeah, thank you as well.
Yeah. And you are always welcome, as I said. Okay, let's see. I just wanna. Obviously, we don't agree, but
it's okay to disagree.
Exactly. There we go. This one. I wonder if I can see this. Skip. Sorry about the adverts.
They're doing my editing.
Okay, let's see. We've got another half an hour before the power goes off. Let's see. Go. Let's see if I can get that. Where is it? There we go. There we go. Okay, I'm going to pause it here. You would agree that oil rig is blocked?
I would say it's compressed. It's because of refraction and things.
Yeah,
so
but the bottom is blocked by water.
It could be blocked because of waves, water, or it could just be compressed. You know what I mean? Because obviously we both agree with compression, don't we?
Okay, so remember the previous Black Swan? Yep. It was also refracted like this. Why does it show the bottom of the oil rig with that one? But yeah, it's also got hectic refraction, but it's blocked.
Oh, I don't know. It could, like you say, it could be waves. It could be compression.
Yeah, but wouldn't that be counterintuitive though? Because you guys claim because of refraction, therefore we can see further. The Earth curve's not blocking it, but now we've still got refraction, and it is blocking it, and we can see the horizon behind it.
Yeah, but we can still tell there's some refraction there because obviously the grains are still ain't straight, aren't they?
Yeah, but that's my point. When you claimed the reason we can see it is because of refraction, now we still got refraction, and it's blocked, and the horizon is behind it.
Yeah, but there can be different amounts of refraction depending on what the temperature is at different locations and what the pressure is.
So then we can claim that it's not physical Earth curve, then it's only optical.
Yeah, it's always only optical, isn't it? Because like obviously you can't see the geometric anything because of the air, so it's always going to be optical.
Okay, cool. So there we go. So the black swan's not a straw man. It is just pointing in the right direction that it's optical and not physical curve.
Yeah, but it's a straw man to say that the geometric horizon. Well, it's not a straw man to say the geometric horizon should be there because that is true. But it's a straw man when you say, well, the horizon isn't there. It's actually further than that because obviously that's ignoring refraction because the geometric horizon doesn't include refraction.
Yeah, the geometric horizon is always going to be 1.22 times the square root of the observer's height in feet. Always.
Yeah, which is fair enough. But if you say it's meant to be this far away and then you see it further, that's ignoring refraction. So you're never going to see the geometric horizon because of refraction.
You can't see a geometric horizon in the first place. You can only see...
Yeah, because
there's only one horizon.
Yeah, but if you took away the air, or you could take away all the air, and that's when they claim you would see the geometric horizon, but because there's air, they claim you can't see the geometric horizon, and it appears further because there's air.
Great. So then I want to ask you another thing. So because it's always refracted, no matter what day, what second, or everything, when we see something blocked in the distance, you would agree then, it's not a physical blocking by Earth curve, it's always optical.
Yep.
Well, yeah, I would agree with that. I mean, they might argue and say, you know, it's their physical curve being lifted up kind of thing, and it's still physical but optical at the same time, but it's optical, ain't it?
Cool.
Do you know what I mean? Like, I'm not going to argue and say it's physical when obviously it's being bent anyway, so it's obviously,
Yeah.
You know what I mean?
No, I agree. But I'm glad you realized, it can't be a straw man because it just validates that it's not physical, because that's the only thing which the black swan is about, to show that the horizon is not a physical blockage, it's only optical, and therefore it's not Earth curve.
I think most globers would agree that it's only optical because we have air. Do you know what I mean? So I don't think most globers, if they're honest enough, would argue that it's you know, physical, because obviously there is air, therefore it is optical. So
yeah, exactly.
If they're honest anyway.
Exactly. Yeah, that's also true if the person's honest. So, any other thing you want to talk about quickly?
I know there's 3 things I was arguing with Nathan Oakley in chat with.
Okay.
There's the black swan, there was the circle of equal altitude. What was the other one?
I have no idea.
Yeah, I can't remember
either.
I can't remember either. My memory's terrible.
Sure. But yeah. But it's good to have
you.
I
think that's it. Shame I couldn't hear the panel as well, but say hello to everyone for me.
Yeah, it's a
I know, that's bad.
They all say hello.
We could have come into Discord, but
we could have come into Discord.
But thanks for having me on anyway.
I really appreciate you coming on, and like I said, you're always welcome in my channel. I just wanted to find out what made you think, you know, to take a step back and stuff. So, but
thanks for being honest with yourself.
Just on that topic before Rachie.
It's like me and you, Annie. We can disagree on that, but we haven't been calling each other names or anything. I mean, people should be able to disagree without be attacking. You know what I mean?
I agree. Sorry, Adam's in. He just wants to ask something. Yes, Adam.
I saw the glass going over an orange. Is that significant to you, Rachie? That demonstration with regards to celestial navigation as an equivalence?
She can't hear you though.
Can't hear you, Adam.
Would you mind?
Could you translate that for us? Because I'm just curious as to that thing we've seen there.
Okay, Adam's
people are perceiving it as an equivalence.
Yeah, Adam is just asking, with that glass over the orange, with the celestial navigation. What is the exact word, Adam?
Is it an equivalence in terms of the circle of equal altitude based on its radius, the amount of distance translated with regards to the surface, be that a flat surface, or as it's placed over orange, the spherical surface? Does it equate to the same distance traveled across the surface?
He wants to know, when you place that glass over the orange, does it equate to the same distance over a flat surface as it would to a spherical surface?
No. I'd say no, because on the globe they'd go around the curve from the top. So if you imagine the top of the orange or whatever was the North Pole, the North Polaris, whatever, then obviously they'd go around the curve, which is a bigger distance than going, straight across if it was flat.
So could I then ask, would that be useful if the distances were different when transposed to a flat plane or a spherical surface? Would that mean there would be a difference if you were trying to navigate using those two different positions that you'd be given?
I think it might be easier for you to come in. Would you mind coming in yet, rather to ask her? If you don't mind, Rachie, can Adam quickly come in?
That's the final question.
Oh, it's his final question. Okay.
That's the point. It's not really at Rachie.
Yeah.
To be honest, it's a point where I've seen that false equivalence used, where they stick a glass, which is perfectly applicable as a circle of equal altitude when placed on a sheet of paper. Yeah. But when you place it over a spherical surface, then that radial value of your circle of equal altitude has an effect.
Yeah.
And that's all I want to point out.
Yeah,
and
he's
shouldn't be mugged off with that demonstration.
Yeah, he's
the
practically
dome
saying,
of equal altitude, isn't it, Adam?
Yeah, he's practically saying the same thing as I did, Rachie, where he says then it's actually a false equivalence, because then if you're keeping it that way, because you say it's not a chord, it would change the distance. So it either has to be a chord, or you can't have the tangents as you placed it.
Well, no, because the tangents would go along that curve where I says it's like longer, so it'll go based on that distance kind of thing. Whereas with the flat Earth, the distance I say, well, it doesn't match geometry. If you was to do the geometry, the angles don't actually match. So that's the problem, I think. Because if you do the actual geometry on it, the angles don't actually match for the flat Earth. Whereas, like I said, with the sphere, they do. I mean, I understand what you're saying with the plane cutting through and the chord and whatnot. But the angles don't actually match the geometry. If you move the distance, the angle shouldn't be the angle that it is for the distance that you move.
Is that Adam?
I'm not sure what excuse me, I'm not sure what that actually meant, if I'm being honest. Could you
No.
expand what you mean when you say if you could move the distance, the angles won't be what?
Adam says, can you expand on what do you mean when you expand the distance, the angles won't measure?
It's like, you have to do the geometry, don't you? Like if you was to do the baseline and move it so far along the baseline and you had a certain angle, say if you measured it at 45 degrees and then that was so much distance from the GP, so if you had it straight up and then you measured it 45 degrees and you know what distance you've moved, and then you keep moving, the angles don't match based on the distance that you move.
The angles.
So if you do the geometry on it, it doesn't work.
Well, I'm a bit confused again. So celestial navigation is based on the angles not matching based on the distance you move. That's how we locate where we are, because the angles don't match the distance. There seems to be a nonsensical response. Flatzoid.
Yeah. Adam, it might be easy if you come in here, mate.
No, this is so much more fun.
It's like playing broken telephone. Anyway, he's saying
piggy in the middle.
Yeah, it's weird because I have to listen to him and then try and transpose it to what he's saying. So you're saying the distances won't transpose the same just because the angles based on the flat are different to the globe.
No, I'm saying it's nothing to do with the globe. If you even ignore the globe, I'm saying the geometry for the distance that you move don't match what the angles should be for the distance that you move. So the angles don't match up to the distance if you do it on a flat surface.
But remember I explained it earlier with that 360 degree circle where we got the degrees, the 360 degrees, to get the nautical miles. Remember I explained it's all based on your vision. When you're looking up in the sky, you would agree we see optically and we can only see so far. So we have a field of vision limitation.
So I understood that as if you was moving around the circle, but if you're moving across the circle like a radius or a diameter across it, then I don't see that working. Around the circle, maybe, but across the diameter or across the radius, like in a straight line across, rather than going around the circle, then I can't really see that working.
Okay, so it's because you're not going around, that's why it won't work. Is that what you're saying?
Yeah, if you was going around, then I could probably see it working. But if you're just going across a flat baseline, like radius or diameter wise, then I can't see that really working.
But that's the problem though, because you have your azimuthal plane on the same plane, it will go across, just like I showed you that screenshot of that other, of them doing the site fix.
Yeah, like I said, my memory's bad. I can't remember which one you mean, to be honest.
But yeah, like I said, go look it up a bit. It will help
I'll have
you.
to rewatch the stream as well to try and, let it sink in and, look a bit more into celestial navigation and that.
Definitely.
Flatzoid, can I just ask Rachie to confirm that she recognises that if you put the glass over the orange, the surface distance is not the same, as placing it on the flat mat.
Okay.
She recognises that point, yeah?
Okay, yeah. Adam's asking one more question. So you do recognise that if you place that cup on a piece of paper, the distances will not be the same as placing it over a sphere.
The distances from the North Pole, say if the North was in the middle of that sphere, compared to on a globe going around from the North going around, no, it won't be the same now.
Happy, Mike? Adam?
Was that a no? No,
Yeah.
they won't be the same.
No, they won't be the same, yeah.
So can I just ask one more question then?
Go ahead.
What's the fucking point of the demonstration?
Adam's asked the same as me. What's the point of the demonstration then?
The point is to show a circle of equal altitude and how it can be done on a globe, so to speak, or a ball. Whereas people are saying that you couldn't get the same altitude, but you can, because like I showed with obviously that's like the circle around the ball, and then obviously I showed the same angle on that circle around the ball, so you can get the same angle from a circle around a ball. So
yeah, but then
when they say that you can't get
but then you would need a cord, which you say they don't use a cord. That's why I said it's not going to work then.
Well, that's what you say. I mean, I say tangent, but like I said, I need to look more into it before I can even argue the point, really. So
definitely.
Does Rachie think a radius can curve?
Michael asked, do you think a radius can curve?
No.
There we go. Yeah, that's simple. Everybody knows a radius is a straight line.
Yep, definitely.
I just want to say thank you, Rachie, for coming on. Really, really appreciate it. Let me know.
Appreciate you having me on, and thank you for being cordial as well. Appreciate that.
Yeah, anytime, and you're always welcome to come back.
Appreciate that. Thanks for having me on.
Yeah, okay. Have a good evening further.
And you too.
Cheers. Bye.
Bye.